This mini lecture is still in Chapter 2 and it's covering Concept 2.3, which basically is covering the major chemical bonds. And the first chemical bond we're going to deal with is covalent bonds. So atoms with incomplete valence shells, they can interact with certain other chemically reactive atoms in a way that each partner completes its valence shell by sharing or exchanging electrons. These interactions usually result in atoms staying close together by attractions called chemical bonds. A covalent bond is the sharing of a pair of valence electrons by two atoms. So they're sharing electrons. This particular figure shows what happens when two hydrogen atoms form a covalent bond. Each hydrogen has one valence electron, represented by the electron cloud, and it has a capacity for filling with two electrons, and that makes it chemically reactive because it's unfilled. So when the two hydrogen atoms come close enough together, their valence shells overlap. So you get this overlapping, and at that point there's two electrons that are being shared. Okay? And this makes a more stable situation where both shells have a pair of electrons, or they're completely full. So this is a stable bond. This is the hydrogen molecule H2, and this is known as a covalent bond. So this figure shows covalent bonding in four molecules, and it gives you an idea of how you represent the molecules. So first of all, you have the name and molecular formula. So in the case of hydrogen H2, that indicates each molecule has two hydrogen atoms. And then electron sharing can be depicted by an electron distribution diagram shown here. And you can have a structural formula where the shared electron bond is represented by a line. Then you have a space filling model, and this really comes closest to representing the shape of the molecule. Oxygen has 6 electrons in its outer shell, and therefore needs 2 electrons to complete the valence shell. So two oxygen atoms actually form a molecule by sharing 2 pairs of electrons, because you can see here 2 pairs of electrons are being shared, and that will be the equivalent of 2 covalent bonds. And in the structural formula you'll see a double line, meaning that's a double covalent bond or double bond. So each atom that can share valence electrons has a bonding capacity corresponding to the number of covalent bonds that it can form. And this number of unpaired electrons in the valence shell is known as valence. So the bonding capacity, the number of unpaired electrons, is valence. And that's the number of electrons required to complete the valence shell. Excuse me, I gotta back up. The molecules H2, hydrogen, and O2, oxygen are pure elements rather than a compound, because a compound is a combination of 2 or more different elements. Now in the case of water, it's a compound. It has 2 atoms of hydrogen, and these are used if they bond with oxygen to complete the valence shell of one oxygen atom. So remember, you have 2 unpaired electrons in oxygen, so the hydrogens can bond and complete the outer shell of both the hydrogen and the oxygen by bonding and forming water. Methane is a hydrocarbon gas. And for carbon, it has 4 unpaired electrons, so it takes actually 4 hydrogens with a valence of 1 to fill the shell of 1 carbon atom which has a valence of 4. So the chemical formula is CH4, and with 4 covalent bonds to hydrogen. So the next concept we'll talk about is electronegativity. So atoms in a molecule attract shared electrons to varying degrees depending on the element. The attraction of a particular atom for the electrons of a covalent bond is called electronegativity. So once an element forms a covalent bond, it may hog more of the electron negative density than its neighbor, if it's more electronegative than its neighbor. So if you form a covalent bond between 2 atoms that are very different in electronegativity, the more electronegative atom pulls more strongly on the shared electrons, and it moves more of that charge towards itself. If you have 2 atoms that have the same or similar electronegativity, they share electrons equally in a covalent bond, and that's going to be a nonpolar covalent bond. The polar covalent bond is where you have electronegativity higher in one atom than the other, and it's going to be an unequal sharing of electrons, shared electrons in the covalent bond. So nonpolar, good examples here would be hydrogen and oxygen, because their electronegativity of each hydrogen atom has the exact same electronegativity, so they're going to be equally pulling on the shared electrons, so that's going to be nonpolar. Same is the case for oxygen. Now for the case of polar covalent bonds. Water is the most perfect example of a polar covalent bond. This happens, so polar covalent bonds happen when atoms are bonded to a more electronegative atom. Then the electrons of the bond aren't shared equally, and the electronegative atom tends to hold the charge more than the other atoms. And this is your polar covalent bond. So the bonds between the oxygen and hydrogen atom are polar. This is because oxygen is highly electronegative. It's like the most electronegative. It's one of the most electronegative of all elements, and it attracts shared electrons more strongly than the hydrogens do. So when you form the bonds with hydrogen, you get an unequal sharing of charge. So you get around the oxygen atom, you get a partial negative charge, delta negative, and you get partial positive charges, delta positive, around hydrogen. And this creates a dipole. In contrast, our molecule methane, carbon and hydrogen are very similar in electronegativity. So the carbon-hydrogen bonds do not unequally share the charge, so they're going to be nonpolar. So methane has nonpolar covalent bonds. nonpolar. The next type of strong bond is ionic bonds, where two atoms are so unequal in their attraction for valence electrons that the more electronegative atom pulls an electron away from its partner. Electrons are not shared in ionic bonds. They are transferred from the valence shell of the less electronegative atom to the more electronegative atom. In this figure, we're using an example of sodium chloride. A sodium atom has a total of 11 electrons in its shell, with a single valence electron in its third shell. Chlorine has a total of 17, with 7 electrons in its valence shell, so it only needs one more electron to complete its valence shell. And that's what happens when sodium and chlorine encounter each other. You get a transfer of the sodium ion of the sodium electron to the chlorine atom, and what that does, sodium then becomes positively charged. It empties its outer shell, so the outer shell is empty. Then its second shell is full, but this leaves you with 10 electrons and 11 protons, so the net electrical charge would be positive. So you're creating a positive ion with a net +1 charge, and this positive ion is also known as a cation. Now for chlorine, you added that electron that was transferred from sodium. Now you have a complete octet, or 4 pairs of electrons in the outer shell, but that gives you 1 extra electron, which would give you a net charge of the atom is negative. So now with an extra electron, you created the chloride ion, which has a -1 charge. And a negative ion is termed an anion. Now that you have the negative and positive charged ions, they are attracted to each other by the opposite charges, and that's the ionic bond. One other feature of ionic bonds is in living systems which are universal solvent in a living system is water. Ionic bonds are weak in water, so they're considered weak bonds in water. So if you have a dry salt crystal, the bonds are strong enough that it takes some mechanical energy, hammer and chisel, to break enough bonds to crack the crystal into parts. But if you put the same crystal in water, it totally dissolves, and it doesn't recrystallize because the ionic bonds are much weaker, because they're partially shielded by the interactions of those positive and negative charges in the water molecules. Of equal biological importance are weak chemical bonds. So we'll discuss a few of those. First will be the hydrogen bond. And so backing up here, our strongest bonds in a living system are covalent bonds, but the weak chemical bonds, which ionic are considered weak because water breaks up the ionic bond or weakens it, and hydrogen bonds are both important. A hydrogen bond forms when a hydrogen atom covalently bonded to an electronegative atom in a polar molecule is attracted to another electronegative atom. So the partial positive charge on the hydrogen atom, in this case water, gets close to nitrogen, electronegative nitrogen, which carries a delta negative charge, and it's attracted to that opposite charge, and represented by a dotted line is that hydrogen bond. That's a weak bond, easily broken, but have a lot of important uses in biological systems and living systems. In this figure is a good example of a hydrogen bond. The other major weak bond is the van der Waals bond. And this happens in nonpolar molecules. But even in nonpolar molecules, you can have asymmetric distribution of atoms that'll have positive or negative charge, but much weaker than even the delta negatives and positives in polar molecules. And you can get attraction of these positives and negatives, and these are van der Waals interactions. Much weaker than even polar hydrogen bonds. Although the gecko is an example of a creature that can adhere to surfaces and suspend itself upside down, and it does that by its feet pads. And in the feet pads, there are these hair-like suction cup structures that interact with wall surfaces and adhere by van der Waals interactions. So one of these hair cells won't hold the gecko, but it has thousands of these on its feet pads, and that's enough to multiple van der Waals interactions to keep the gecko from falling. The last concept is molecular shape and function. So molecule shape is very important to its function. Molecular shape determines how biological molecules recognize and respond to one another. A molecule consisting of two identical atoms, such as our hydrogen and oxygen, H2 and O2, are always linear, but most atoms with two or more atoms, compounds, have more complicated shapes. So compounds will have more complicated shapes. The water molecule in this case is V-shaped, and with its two covalent bonds spread apart by 104.5 degrees. The methane molecule has a tetrahedron shape, so this is a pyramid with a triangular base. And in the center of this tetrahedron is the carbon, and radiating outward are the covalent bonds to the hydrogens. And the hydrogen atoms are in the corner, at each corner of the tetrahedron. So the last concept, biological molecules recognize and interact with each other with a specificity based on molecular shape. They are synthetic molecules with similar shapes, and they can mimic the biological effects of a natural molecule. In this case, the synthetic molecule morphine affects pain perception and emotional state by mimicking the brain's natural endorphin molecule. So here's the synthetic morphine, here's the natural endorphin. Notice the box area, they have a similar structure, and both of these structures can bind to the same cellular receptor, and that will produce similar biological effects. The last concept of this mini lecture is 2.4, very brief, chemical reactions. And basically, you have reactants that react to form products, And all chemical reactions are reversible, so products of the forward reaction become reactants for the reverse reaction. And chemical equilibrium is reached when the forward and reverse reaction rates are equal. Thank you for your time. This concludes Concepts 2.3 and 2.4.